Okay, so let's review the basic milling toolpaths. So we have face, 2D contour, and 2D pocket. These are the main toolpaths that you're going to use on milling. In drilling, but we're going to focus more on. Drilling's pretty simple. We've covered that. We're going to focus more on facing, pocketing, and contour. Okay. Now, there's obviously more toolpaths, but most of the time you're going to use, facing, pocketing, and 2D contour. Those are like the main toolpaths you're going to use in drilling. But these other toolpaths, they have their time and place to use them. So 2D adaptive clearing. You're not always going to use that toolpath, but it's a great toolpath to have in your toolbox because it can, it gives you more options. It's a more optimized toolpath it's good for applications where your stock, where the stock versus compared to the material that needs to be removed makes it more difficult to get a well optimized cycle time. Basically what I'm trying to say is you're going to have like air passes and stuff on basic 2D contours on certain parts, so it's a more optimized toolpath. I'll show you what I'm talking about later. But so facing, 2D contour, and 2D pocketing. All right. So let's go ahead and do a setup. So I'm going to go ahead, I'm going to create a setup. We're going to be on milling, your model orientation. So we're going to select the Z axis and the X. All right. So I click the top of the part to reference my Z. If I zoom in, notice that the stock is above the part face. Okay, just keep that in mind. All right. So you can see our X already popped up in the right direction. If you needed to change the X direction, you just click on X axis and you pick a segment or edge that runs parallel with the where you want the axis to be, like this, and you can see how the X kind of jumped perpendicular. But anyways, I'm gonna move the X back because we're holding it in a vise, and a vise is gonna hold the part better, like this. Okay, so how about this? On this example, let's just make our stock 0. And now notice that the Z is on top of the face of the part. All right. That's because the Z is going off the stock instead of the model. All right. So when I brought the stock to 0 relative, the stock now lines up with the outer boundaries of the model, basically. All right. So, and let's move our stock point over here. And if you like to, you don't have to put it in this corner. I always put in that corner because on a vise, your work holding is more repeatable if you have your origin against the fixed jaw of the vise instead of the moving jaw. All right, so keep that in mind. But if you want to have positive X and Y values in your G code, you know, you can put your origin right here if it goes. Okay, so Fusion 360 recently did some updates. I feel like I say that every week. I had this problem the other day. The origin wasn't really wanting to locate in the right spot. Also, notice I have these planes right here. I don't know what's making those planes pop up. Let's see. Okay, we'll just leave it there for now. But you can move the origin over here, and the benefit of that is you get positive and XY G code values. You know, so all your positions are in positive numbers, right? If you have to do any kind of editing on the G code, it makes things a lot easier. I always name these, even if it's one operation, I still name it off one. It's just a habit. I don't know. I like, you know, I feel the need to name the operations, even when I don't have to. Now, you usually want to kind of name stuff and organize it, so when it posts the G code, you know what's what. And if you open up the file later on, you know you can distinguish what's going on, different operations and different toolpaths. It makes things a lot easier. Now, we've mostly focused on simpler parts because, you know, this is more kind of an introduction to learn CAD/CAM. But once you really start using CAD/CAM like all the time, you're going to do more and more difficult parts, right? So you're going to have a ton of operations or a ton of toolpaths. So this will quickly fill up your screen. And you'll have so many different toolpaths, and you'll find yourself like clicking on different setups or different toolpaths, trying to figure out what's going on or trying to look for stuff. So I would just get in the habit of naming it, and you know, kind of take it from there. If you name these, it just makes it a lot easier. Okay, so I got my setup. So we're gonna go over facing. Now, there's one thing in here. I don't know if Fusion 360 made any changes on facing since the newest update. So we're going to pick a facing tool. So I'm going to go select. And I'm going to use my face mill filter. All right, so what you'll notice is no tools showed up, right? This is just a filter. Now notice what I'm actually viewing here. I'm trying to find a tool, right? I have no tools in here. Why not? That's because I'm currently looking into this specific document, right? If I go to my library, I have a 4-inch cutter right here. If you go on the Fusion 360 library, oh wow, there's only 2 cutters in here. Okay, so if I go to the Fusion 360 library, notice all the tools that pop up. I got a ton of them. right? So keep in mind when you go into your tool library, or you go to select a tool. If you can't find a tool, first make sure you're looking in the right place, because this is more of like a view window of what's in this specific location. Okay, so you have the default Fusion 360 library, a local one, and I have my sub-local libraries. Like this is my own library of tools that I use consistently. And then at the school, this is tool sizes and numbers that we use at the school. And so yeah, I had, I'm on my filters on for milling, but this would be the lathe tools. Okay. Now you don't see any lathe tools because I have my milling filter on, so it's kind of filtering out those tools. But anyways, so if you can't find the tool you're looking for, first check the location that you're actually viewing, and which library you're working on, and then check your filters. So I'm gonna go to milling, and I'm gonna filter out everything besides face milling, and I'm gonna search within the Fusion 360 library. All right. So I got two choices here. I have a 50 millimeter face mill and a 2-inch face mill. All right, so we're in the U.S., so everything's imperial out here, so we'll use this 2-inch face mill. So I'll go ahead and select that. And if you're, this is more of a exercise on, the toolpath itself. If you're actually going to be facing, I would suggest, in the Fusion 360 library, I would double check the speeds and feeds. Let's see, 2-inch, 6,500 RPM. It's kind of fast, but yeah, let's do it. 65 feet rate. This is actually not bad. Sometimes the speeds and feeds can be we'll just say excessive. Okay, what was it doing? Okay, like I said, they made some major updates earlier. Everything's kind of grayed out, and it's in read-only mode. Okay, let's exit out of this. I don't know why I was doing that. I don't know if it was a bug. There's usually some random bugs every time they do a major update. All right, let's try this again. Oh, I don't usually use tools in the Fusion 360 library because they're default tools. Okay, so you used to be able to edit these. I think I usually just create tools because I find it actually faster to do that. But anyways, it won't let you edit that tool. That's why it wouldn't let me change anything. But I could copy the tool. Okay, we'll come back to this another time. But anyways, the speeds and feeds look good. We're going to go ahead and go with this cutter. right, so I'm gonna go to geometry and notice the highlighted box around my part, right? So that's the stock contour. So in your setup, if you if you had your stock settings being bigger than the actual 3D model, that box would extend out. Okay, it's basically showing the fence line of the stock. So we're gonna go ahead and we're just gonna leave it. You don't even have to click anything on that. Facings is actually pretty easy. If you're having trouble with facing, it's either your stock settings or you're trying to do too much. Okay, and you change something. I mean, you could almost select a tool and tell it where where to stop cutting at. Your bottom height, and hit OK, and you have a toolpath. So I mean, select a tool, select where it's going to stop at, and it'll give you a pretty good functioning toolpath. Depending on how much stock you actually need to remove. I mean, if you got to cut off a half inch off the face, you definitely don't want to do that. You'll have some bad inserts on your face mill. But anyways, so I'm gonna go to the height, and yeah, model top's fine. I can actually just hit OK. Fusion 360 is pretty good. Actually, most CAM software is pretty good at doing face operations with with minimal input. Like, you don't have to give it too much data. Like, here's my stock size, here's the tool I'm using, here's the model, and it'll face it. Now, when you have to take incremental passes, incremental Z passes, where you have different depths of cut, yeah, you want to make sure you supply the software with the right data that it needs, or information. But anyways, you usually do that within your stock settings. Okay, so here's our toolpath. What I'm looking at, I like to make sure the toolpath is going to start to the side of the part. And I like to make sure that it's going down to the top of the model, all right? Because sometimes it may look like you're on top of the model, but if you were to zoom in, you'd realize that you're not. And, it has to do with something that it has to do with the information you supplied to the software. Either your bottom height on your height tab, or you could have one of the settings on, like save stock material for the Z. But anyways, save material for the finish pass. Okay, so there's our toolpath. Let's simulate this. In the last state of Fusion 360, they had the simulator going a lot faster than usual. So we're going to slow this down right here. Now remember that the purpose of the simulation, it doesn't really do anything. It's just a tool so you can basically verify that your toolpath is correct. Because if you didn't have this, trust me, there's a lot of you could have gave the software the wrong data points or the wrong settings or parameters to calculate that toolpath. All right, so this is just verifying that, for the most part, verifying that you put everything in right, and that it's, the tool's not going to crash into the part. That's what you're trying to avoid. You want to avoid crashing the machine, and you want to avoid breaking tools or junking parts. You also want to avoid wasting time, but Okay, so that looks pretty good. So that's our face operation. So now we're going to do a 2D pocket. All right. Now, this tool won't fit into this pocket, so there's no way I'd be able to generate a G code, a toolpath right there. You know, the software wouldn't let you do it. I mean, there might be like a back doorway, but you know, you kind of want to look to get a good toolpath. So I'm gonna go to my tool. And I'm gonna use, we'll say we'll use an end mill. I used to have more tools than that. Okay, we'll check in our Fusion 360 library. So what I'm gonna do is I'm gonna put my flat end mill filter on. All right, so these are all the flat end mills I have. Notice some are in metric, some are in inches. And I'm gonna use a filter and filter out a specific diameter or range. We'll say we're going to use a 0.75, so 3/4 end mill. All right, so notice my window or my dialog box for the tools. So it updated, and I have 2 end mills to pick from. I'm just going to use this one. Now that last tool, the face mill was tool number 2. So what I'm going to do is I'm going to change the tool number. Okay, you can't change it. Yeah, they get these on read only. Here, we're just going to make a tool. I usually have more tools than this. What you'll notice is sometimes when they do a major update, you know, sometimes your tools are gone and you have to remake them. Now you can save them or export tools. So there's ways to back it up. But anyways, so I'm going to do a flat end mill, 0.75 inch diameter, 0.75. I'm going to hit tab so it updates the shaft diameter. And by default, it just makes that equal whatever this is. That's all I'm going to change. Cutting data. I'll go. Actually, y'all are using a VF2. Let's just crank it up to, I don't know. We'll say we're using a 2-footer end mill and cutting aluminum. So we're going to go fast. Cutting feed rate. Yeah, we'll start off at 40. Now remember, these speeds and feeds, you probably asked yourself by now, you know, how do I know what speeds and feeds to actually, you know, to make the machine cut at? I'm gonna be honest. There's no like easy answer. What that, you know, you don't really want to think. I mean, you wouldn't be thinking what speeds and feeds are you going to use, but you really want to look at them as starting values, okay, or estimates. So unless you now there is software that will calculate all this stuff for you. There's some pretty good software for that. Was it G? I think it was G Wizard. But anyways, so these are starting values. So when you input these feed rates, I would just aim to get something close that you know that's not going to junk apart or break the tool. And when you initially set the machine and run your first part to prove out the program, what you're going to do is you're using these as starting values. Okay, so it's just a feed rate to start with, and it's just a spindle speed to start with, right? And as the machine's running, you're going to observe, how the tool's performing, how the chips are coming out, the color of the chips, how much heat is generated, transferred into the shaving. The color, if you're cutting steel, or it might be hard to do on aluminum, but on most steel, you could tell how much heat is being generated or is being transferred into the shaving, which you want it transferred to the shaving. You can tell by the color of the shaving, right? You'll get like a golden tint. It could turn blue or red, orange. You'll have some colorful shavings sometimes when you start getting heat transferred into the shaving. But anyways, so these are starting values. So this is just to give you. Don't worry about getting this perfect. Just get it close, and when you put the program on the machine, you observe, you watch how the tool is performing, you listen, and, for resonance. You just got you got a high pitched chatter noise kind of vibrating there in the room. That's resonance. So your tool or the workpiece, something's moving at a frequency. Okay. But anyways, and you adjust, as it's cutting, you observe and you adjust the feed rate, and you kind of dial it in. Think of it as tuning a guitar. You're not going to tune the string before you pluck it, because you need to pluck the string so it gives you a starting point to adjust to that perfect note. Okay. Maybe not the best metaphor, but I used to play guitar a lot, and I don't know, it kind of makes sense for me. If you're a musician, it would make sense. But okay, so I wouldn't worry about vertical feed rate, because you're not really plunging into the part. You're not feeding just in the Z move like a drill. You're gonna have some kind of ramp or a lead in. We'll go ahead and change it to 10. All right, so anyways, the face tool was tool 2, so we're gonna make this tool 3. I like to try to keep my tools in sequential order. It makes setting up go faster and simpler, and depending on how fast your tool changer is, it makes changing tools faster. Now, if you work at a nice machine shop, you'll probably have a mill that's very quick, like competitive tool changing speeds. Okay, so anyways, I'm gonna hit select. That's the tool I'm gonna use. So I'm gonna go to the geometry tab, and I'm gonna select the contour that I'm gonna be cutting, to define the pocket operation. All right. And make sure you have your arrow, this red arrow. So basically, I selected this geometry, right? If the arrow is on the outside of that geometry, that means it's going to cut on the outside of that geometry, right? If the red arrow is on the inside, that means it's going to cut inside of this contour, or this selected, these features. And to switch, you just click on that red arrow, and it's going to jump back and forth. All right, height tab. So the most important thing on the height tab is telling the tool when to stop cutting. Okay, so you got to think, how deep are you going to cut? You know, when you're through, what's the maximum Z depth? So I'm gonna go to my bottom height, and I'm gonna put this on selection, and I'm just gonna click on that floor. All right. I like to jump into a side view so I can visually see. Sometimes if you're at the wrong angle, you know, it may look right, but if you put it in like a straight front view, you know, you get more, you get a bigger picture of where it's stopping at and where it's starting at. All right, so passes tab. So I'm going to put it on multiple depths, and or say we're cutting aluminum. I forgot how deep that part is, but we'll say we'll cut 300 thousandths deep. Now you might be asking yourself, how did you know to put that? Okay, well, for one thing, that there's a little bit of guesswork in that, but also this is where having some experience helps. And how you get experience is, you know, you run more parts, and when it's running, you're gonna observe and watch, you know, how the tool's performing, how the chips are coming out, and how does it sound. You know, you can tell a lot by sound. So there is some guesswork. What I would do if you're just starting off, you know, just ask somebody that knows. And if you're not sure, it's better to go too shallow than too deep per pass. Okay. So if you can keep it less, you know, you're less likely to break a tool. You may just waste some time. It's going to take longer, but you won't break a tool. But if you go too deep per each incremental depth, then you're just going to break a tool or junk apart. But anyway, so I'm going to put it at 300,000. So there is some guesswork in that. I'm cutting aluminum with a 2-fluter end mill. So I don't know. To really know what specific depth it needs to be, you need to have some software or a lot of data, you know, on, you got data on your tool, data on the material. But anyways, so I'm gonna put this at 0.3. Stock to leave, radially, I'm gonna leave 0.01. Actually, I'm gonna put it at 0. Okay. Now, what's the difference between radial stock and axial? Okay. Now this brings us to two concepts in CAD/CAM, or just CNC machining: radial and axial. I think I have a document on this. We'll pull it up later. But for now, the simple answer is radial is going to go off like, you know, your X and Y, like the radius of the cutter. Axial is going to be your Z. So you're saving material in the Z. Radial, you're saving material per side. So, you know, like the side of this wall, you would save 10 thousandths. Axial, it would be saving material like on this floor, okay, or the bottom of this pocket. And I'm putting that at 0. And the reason why I'm putting it at 0 is because basically we're kind of reviewing basing, 2D pocketing, and 2D contouring. You know, your main toolpaths. I don't think we need to do drilling. Drilling's pretty simple, but some of these toolpaths are pretty simple once you kind of understand, you know, how everything's set up. But anyways, because my finished pass is going to be a 2D contour, if I saved material on the axial stock, what would happen is, the 2D contour is just going to cut along the wall, right? So, you would have material on the floor that didn't get cleaned up. Okay, so with that in mind, I'm putting my axial stock as 0. Okay, so sometimes the best thing to do is try not to overthink your toolpaths. Now, when I say that, if you're actually going to run the part, outside of this tutorial, I'm sure you're not going to run this part, but outside of this tutorial, you do need to double check your speeds and feeds, and you don't want to go in and cut apart. You don't want to run a program. You hit cycle start and it crashes into the part and breaks the tool. So keep that in mind. But sometimes it's the best thing to do is not overthink these and just hit enter and look at the toolpath it gives you, if it gives you a toolpath. So this is the toolpath it gave me, right? So to really get good and understand like what needs to be put into those parameters or what's like useful settings, you need to get used to looking at the toolpath it gives you, and you want to try to distinguish what, how that configuration of that toolpath, like what's making it do that, right? So we got the spiral red toolpath, the helical red toolpath that kind of ramps into the part, right? Then you got these blue ones. There's 3 levels of them. So this red helical toolpath, that's your lead in, right? So it's calculating the lead in. It's calculating that from the linking tab, and it's also getting the starting point. It's getting some of that data to calculate, to compute through the algorithm they use, or series of algorithms. They need a starting place. So the feed height and top height, that's also involved too. So let me give you an example. So if you look at the distance from the top of the part to where the helical lead-in starts. Okay, so you look at that distance. Now, if I change this top height or feed height, I'm going to change this to, I'm going to have this a little exaggerated so it's more, so you can see it better. So I'm going to put that at 20 thousandths. Okay, so we had a little bit of conflict right there. I made it, basically, there's some constraints. To put it in CAD terms, I over-constrained my toolpath. Alright, so here we're going to reduce this to 20,000 as well. Basically, this distance can't exceed this value. Okay. Also notice now my ramp clearance over here. Notice that's red. Okay, so here let's hit OK and see if it generates a toolpath. Let's just ignore it. So it still generated a toolpath. It didn't actually do what I wanted it to do because it kind of ignored. There was conflicting information that I was giving it. All right, so ramp clearance helix. Okay, so warning, some of the ramp clearance height and the vertical lead-in radius is higher than the feed rate. Consider reducing the ramp clearance height or the vertical lead-in radius. Otherwise, the feed height will be raised to match the sum of these values. Okay, so I forgot. This needs to be reduced, right? Nope, still red. Okay, hold on. I usually don't have problems with this one. I kind of changed it up just so I can explain things, and so I'm doing things a little bit out of my normal routine. Because I was trying to give you all an example. Feed height, 20 thousandths. Safe distance, 20 thousandths, and it needs. Here, let's just input something. Okay. This usually works pretty good. Here, let's change this. Here, let's just make it 0. Sometimes you got to play with these values, or the data you're supplying it, and it's kind of a pain at first. I mean, sometimes I still have trouble. Like if they do, Fusion 360s, they're always making updates, and sometimes they'll change the process, and sometimes it's user error. Okay. Some of the ramp clearance height and the vertical lead-in. Okay, so the vertical lead-in radius. Okay, so I think we need to do. Let's do this. We'll change this to 20. And we'll make this 0.1. But we'll also. Will that work? Okay, so notice we're not in the red anymore, so it's good. So basically, the math didn't add up, or added up. It added up too much. It was. I had this at 20 thousandths. So the sum of the vertical lead-in radius and the ramp clearance, those two added together can't be higher than the feed rate. But anyways, we'll say okay. That was like a little 5-minute detour. Okay, so what I was trying to show y'all is if you put it in a side view, notice where my starting point of this helical lead-in. Notice where it is now. It was up here. Now it's down here. So you have, if you observe and kind of look at the toolpath is giving you, and just take note. Notice the colors. All right. That's different parameters within the settings. So this is your lead in. This helical lead in. That's usually going to be input information from your linking tab. Your lead in and lead out. But anyways, just watch like the toolpaths it gives you, and kind of do a little bit of detective work. Try to see what was it that was in these settings and parameters that made a toolpath look like that, or be a certain distance, or that's just my suggestion on getting used to CAD/CAM software. All right, so let's go ahead and simulate this. So okay, so what I like to watch, I like to put it in exactly top view, or specifically top view, and I like to watch and make sure that the tool is starting to the side of the part, just slightly. You don't want to go too far because then you increase cycle time. But you don't want to get too close because if the saw guy screws up and cuts the stock a little bit longer than the previous part, you could kind of wrap it or crash into the side of the part and possibly damage a cutting tool. We'll speed this up. So I like to see the starting position, and I like to watch and verify that the Z looks correct, because it's easy to accidentally click and select the wrong reference geometry or setting. It happens. There's a lot of stuff you have to supply the software, and it's easy to make a mistake. But yeah, so I verified that my height for my my total depth, which is actually just to the top of the part, that looks correct, and my starting point looks right. I also watched the ending point, but on a face operation, it's not that critical. When it's through facing, the tool goes up. That's all that matters. But if you're checking your maximum Z depth travel, you don't have to worry about crashing in the part, because it's not going to travel past the Z depth. How's it going, man?
What do you think I should back off on for running that for the first time?
How much did you adjust the tool? I noticed we were down like 20 thousandths or something.
Yeah.
Dude, I would. So you just set the tool on top of the board? I mean, it's going to take longer, but we're already past halfway done on that part. Dude, I would just put it back at 0. Yeah, we're going to have to rerun it a few times anyways. Yeah, you can put the height at 0. Yeah, either way, we're still going to... You're going to have to run that like 3 times before you dial that distance in. Okay, so if we look at the pocket, this is the pocket operation here. Let's go back some. And you could simulate the whole set of toolpaths, or you could simulate an individual one. If you right click on this, it simulates everything in that operation or setup. If you right click on this one, you can simulate just that specific toolpath. All right, so that went by pretty quick. And remember, the goal is to verify that the toolpath looks right. So You know, a lot of new CAD CAM users, I noticed they'll be like zoomed out apart. I mean, they'll be like 10 feet away. And they're like, yeah, it looks fine. It gets all right. And it's like, dude, zoom in because you want to verify that it looks correct. So make sure you zoom in. You want to get fast and like efficient at, you know, at zooming in, zooming out, and panning and rotating. But anyways, so this is going to helical spiral down to the second pass. So it's taking 300 thousandths depth of cut. So now it's taking 600 thousandths depth of cut. So it goes in 0.3 increments down until it reaches the floor of the part. Also notice these corners, the radius on here, how there's stock still in those corners. You know, just remember that you have a round cutting tool. A round cutting tool is not going to fit all the way into the intersection of that corner, right? It's mathematically impossible. Yeah, so it's mathematically impossible to get rid of that radius with a spinning cutting tool. You know, you'd have to EDM it out or water jet it out, or reorientate the part. That requires another setup. The best thing you could do is try to minimize it. Okay. Now I'm using a 3/4 end mill. The smaller the end mill I have, the smaller the radius is going to be, which will mean the smaller the distance from here to where that radius goes to. So it would make it less of a radius there. All right. Yeah. Uh-huh. Yeah, you really can't. Not on this part. Sometimes you can get creative and like reorientate the part, but you have to have. It depends on the shape of the part. Like this, you know, I couldn't reposition. You know, I couldn't reorientate the part in order to get a flat down here. Sometimes you can, but the best thing to do is just try to minimize how big that radius is. Now there's other methods too. What some people like to do is they'll actually drill out these corners, and then you're going to have like a hole that exceeds that passes up this intersection right here. So it kind of looks funny depending on what size drill you use. The bigger the drill, the worse it looks. But that's one method. I don't really like that method, but you know you gotta do what you gotta do sometimes. But you're always gonna have some kind of radius there on a operation like this with a spinning cutting tool. You know. Now, for example, say that you didn't have the side of this part right here. So all this was open right here. Then you could drop it end mill. You know, if you had your part standing up like this, you could drop it end mill down and cut. You know, cut across, and you wouldn't have a radius there unless your end mill had a radius on the cutting edge. But you could do that, but that requires another operation and setup. So, you know, your cycle time and your time of manufacturing and cost of manufacturing is going up. But anyways, there's no way to really get rid of that radius. in this current setup. So we're going to try to minimize it, right? So this was a roughing operation. So now I'm going to go to a finish. Now you notice there's no finishing right here, but what there is there's a 2D contour, which 2D contour, you know, you could think of it as a type of finish pass. It's really not. It's like a modular toolpath. I mean, it can be configured to whatever application you're doing. This is the edge I want to cut along or drive the toolpath and cut it across. You can tell it to take it more depths or more passes. You can go through the settings and it's kind of customizable, but you can think of it as a finish pass because you're going to use it to finish the part. But anyways, so I'm going to use a smaller end mill. All right, so let's say, well, really I want to use a 3/8 end mill. So we use tool 2, tool 3, and now we're going to use turret position 4 on this. So I'm going to go flat end mill. We'll do a 3/8 inch end mill. 3/8 of an inch equals 0.375. I'm going to hit tab to jump down so it updates that shaft diameter. And you can see how that changed to equal this sum. And I'm going to go to the cutting data. Let's just go with that. And we'll make this number 4. All right. And what I usually do is I select the tool number and type in a value, 4, right? Instead of actually clicking on each one of these, if you just hit tab, it'll jump down. And this value by default is going to equal the tool number, right? You could change it if you want to, and it'll do something different, or you can leave it at that. So I'm gonna leave it at that. I'm gonna hit tab and see the number, offset, leaf offset, and diameter offset. They're the same values. You usually want those to be the same. So I'm gonna hit accept. Yes. Uh-huh. Yeah. Okay. So what was probably going on in that exercise? What we did was we made the stock going around 0. Or were you using 2D contour? Huh. You might have used a different one. 2D contour, you can put your stock at 0, but some of the toolpaths, if there's on some of the toolpaths, if there's conflicting information, like if you're trying to remove stock, but in your stock settings you say that there's no stock to remove. If you make the stock match the model, the software will think that there's no stock to remove. So on some toolpaths, it won't give you a it won't give you a toolpath. It's probably some type of conflicting information. To be honest, I really can't tell you what's wrong without actually seeing it. If you email it to me, email it to me and put some kind of notes on what happened, and I'll download it and open it up and check it out. But yeah, we'll do that. And those exercises, you only have to drill those. Was it the first exercise with 3 parts? So it was like a 1-inch square with no. It was a 2x2 square with a 1-inch hole, and then the 2x3 square or rectangle with a 1-inch. Okay, so that one you only have to drill it. So you actually don't have to cut along the outside. Now, if you want to, make sure you use 2D contour. Oh. Okay, the third one, the third one was round, right? Yeah. I think it should cut it. What I would check is check your height tab on it. Over here, let me walk back over here. Guys, I might lose y'all for a minute. My battery's wanting to go dead. Yeah, I'm gonna try to answer this question real quick, and then I'll grab my charger. Okay, so what you need to check, I would check the height tab, the bottom height. If you don't actually select a bottom, sometimes it won't give you a toolpath, or it'll give you a toolpath that's above the part. It doesn't go below the face of the part. So keep that in mind. But that's what I would check. I would check this bottom height and make sure it's actually, it actually has some depth in there. Okay. Hey, hold on. Yeah, hold on 1 second, man. My laptop was about to die. Let me grab this charger. Hey, are you guys still there? Oh, cool. My laptop actually died and turned off. That's kind of cool. I just turned it back on. I got the charger. It's plugged in now. WebEx did a good job. That was kind of seamless. Like, my laptop literally turned off, and I turned it back on, and we're still in class. Huh. Cool. Okay, so yeah, I would check if you're not getting a toolpath, and it's on the outside of the part, I would check the bottom height. And if you're not getting a toolpath and it's on the inside of the part, I would check your linking tab and make sure you have room to actually lead in or drop the tool down, like there's enough room in there compared to the tool diameter. But basically, you need you need some type of clearance to actually get the tool in there. So you're having trouble getting on internal features. I would check your settings, like how much, if you're saving stock, how much are you saving, and check the input values on the linking tab. For example, this linear lead-in distance. If you have, say you have a pocket that's 1" in 10 thousandths wide, right? So 1" in 10 thousandths wide. And this is an exaggerated example to kind of prove a point, but you have a pocket, it's 1" in 10 thousandths wide, right? Now, say that you use a 1" end mill to cut that out. Now, there might be a better option, but this is just an example. So, you know, if the future is 1" in 10 thousandths wide, and you're using a 1" end mill to cut it out, you only have 10 thousandths clearance. All right. Now, with that said, if there's only 10 thousandths clearance and your lead-in distance is 37, you're going to have problems. If your linear lead-in distance is at 11 thousandths, you're going to have problems. Now, say your lead-in distance is 5 thousandths, that would work. But if your linear lead-in distance is at 5 thousandths and your horizontal lead-in radius is at, say, 6 thousandths, that equals, those two, the sum of those two equal 11. So you don't have enough clearance to get that tool in there within, that 10 thousandths clearance. But with that said, that's some of the stuff you got to watch out for, especially internal features. External features are usually easy. You usually don't have too many problems with that. Internal features, you have to think about tool clearance. It's hard to cut something if the tool can't actually fit in there within those parameters and cut it. But yeah, I would check that out. So okay. Yes, 2D cutter. Yeah, no problem. All right, take it easy, man. Okay, so we got our tool. So I'm selecting my geometry. So I'm just gonna drop the tool in and finish. Okay, so I saved 10 thousandths per side when I did that pocket operation. And so I'm coming in and I'm removing that material that was saved. I'm also removing the material that was in these corners. I won't be able to remove it all, but I'm using a smaller end mill, which means I can get closer to this edge and minimize that radius that's there. So there'll be less material that's still in those corners. Now, usually, whoever's ordering the parts or designed the parts, usually they're aware of stuff like this, unless they never dealt with a machine shop. They're probably not aware of it. Like if you have a buddy that's a mechanic and he's like, "Hey, dude, can you make this part?" You might want to inform him that when the part's assembled, there's going to be stock left there that you're going to have to either make the pocket bigger or another solution. Now, most people who order parts from machine shops, they've already ran into this. Like it's one of the first problems you run into when you start machining or you start hiring somebody to machine stuff. It's like, okay, I need you to cut this. So most designers or engineers, they're aware of this, and the part futures and how, if there's something that's going in here, like more than one part being assembled, they thought ahead about this and they designed around it. Okay. So they're aware of it and they design around it, or they'll put a tolerance like maximum radius 1/2 inch or 1/4 inch. So you have to do it 1/4 inch or smaller. But with that said, I'm gonna go to my hype tag. I'm gonna make sure, now I'm just doing a finish pass, so I'm gonna drop the tool all the way down to that floor right here. And so there's no need to do multiple passes. And this is the finish pass, so I don't want to have stock to leave check. It wouldn't be a very good finish pass if I was still saving stock. And that's pretty much it. These, on a finish pass, using 2D contour, these settings, these preset settings that are already in here that Fusion had by default, they should be fine. I literally hit OK and come over here and verify it looks good. Now you'll notice now the part looks a lot better, and you'll also notice these corners right here, that radius is a lot smaller, okay? But, okay, cool. Okay, so we did our face. We cut the pocket. That's a roughing. 2D pocket's more of a roughing toolpath. Now, it could be a rough and finish toolpath, but keep in mind, one of the limitations on pocket operations is you can't put a G41 or G42 tool diameter or wear compensation code in there. Okay, and let me show you what I'm talking about. So 2D contour, we're gonna go to 2D contour for a second so I could illustrate what I'm talking about here. So I'm gonna post just this 2D contour. Okay, so if we look at this code, oh man, I didn't have the setting on. So these are called preparatory commands, and it's basically preparing the machine. It's canceling any previous offsets that could have been turned on. So here's the actual toolpath. So it grabs tool 4, turns the spindle on 5,000 clockwise. Activates G54 work offset, turns the coolant on, goes to this, it rapids to this position to get close to the part, and then it feeds down and turns on tool height offset 4, and it goes down to 200 thousandths above Z0, or above the face of the part. Then it feeds in closer, so it gets really close, and goes to a starting depth, okay? Is getting in, basically is feeding into position to make a movement, to make a radial lead-in movement right here. So on the linking tab, that radial lead-in, that setting right there affects where this starts, okay? So it's gonna feed down into position to that starting point to do that radial lead-in. And then right here, that's the linear lead-in distance. Well, it's not the distance, but whatever that distance was, that's where it's coming from, and it's feeding to the part itself. then it starts cutting right here. The tool engages and it's going to walk around and cut. And then right here, it's going to, right here, it leads out from the part, so the tool is no longer engaged, and it rapids above the part, and then kind of slowly prepares everything to turn off, pause the machine or whatever. Now, what it didn't do, here, let's close some of these. What it didn't do is it didn't give me a G41, G42 compensation. All right, and let me show you how we add that. So on finish passes, or to be honest, I generally like to use this all the time. If I could, I would suggest, I would just love to have the software to automatically put a G41 or G42 compensation offset and everything, but it doesn't. Okay, and there's reasons why. It isn't like the programmers are just lazy and they don't want to. They're like, no, you can't have a cutter comp in roughing passes, because sometimes it's helpful. But it also, having a work offset compensation adds limitations to your other toolpaths. So they don't have it on every toolpath. They have it mostly on finish passes. You wouldn't want it on every pass. I mean, you may want it, but it brings up other issues. Okay, there's other conflicts, and it's not the solution. But anyways, so on the finish pass for 2D contour, if I go to edit and I go to this passes tab right here where it says compensation type, if I put it on where, and here's one of the constraints right here, is this compensation radius. This parameter specifies a range of tool diameters that can be safely used. When it says safely, basically there's enough clearance to get the tool in there and do what you want to do and compensate. Because I'm going to exaggerate this as an example. If you compensated the tool to cut an inch off, but you didn't have clearance for that compensation value, it could either gouge the part or, hit, you could junk the part, or, a nice way to put it, you could modify your vice jaws. You can either break a tool, crash the part, you're going to screw something up. Okay. Long story short, yeah, you'll probably screw something up. But anyways, so this is like a constraint, or it adds more limitation. But anyways, we want to put a G41 in the code, right? So in case the cutter is too big or too small, we can adjust it on the machine without having to repost the G code. With that said, you want to go to where, and I wouldn't change this unless you know what you're doing. I mean, and it's good to experiment with that, but I would just leave that wherever it comes up, unless you have issue, is causing other issues, and then you got to figure that out. But so I'm going to hit OK. So I changed the compensation type. Instead of in computer, I put it on where. So when I post process this, okay, so I went over the structure of the code earlier, and what's going to be different since I reposted it is, where'd it go? Right here. All right, so after the tool gets in position, the machine's on, and it kind of the tool drops down and gets in position to make that first to make that first initial tool engagement into the stock material. It's going to turn on your G41. Okay, that's going to activate any compensation offsets, tool wear offsets that you input into the machine. Now, if you don't need to compensate, you just won't input anything into the machine, so you can ignore it. But it is a good habit to make sure that the person who used the machine before you didn't input something in the tool wear and forget to clear it out, because then this could actually cause you to junk your part. So keep that in mind. But if you're going to use tool comp, tool compensation, you need to know how to use it. If you never used it before, sometimes it can be a little tricky. But anyways, you need to kind of read up on this. But we'll save that for CNC class. But that's how you put a tool comp in there. If you're doing a finish pass, I would suggest having a G41, in the G code. So you want to turn on. Here, we'll just go over this quick. So in the passes tab, your compensation type, wear. Okay. By default, Fusion 360 does it in the computer. And what that's doing is basically, if you select this line right here and you're going to drive the toolpath off that, your toolpaths are actually, the math is based off the center of the tool, right? So if you're using a 1-inch end mill and you didn't have it on in computer, you get it off, your part, and you're driving the toolpath off of this segment, your part would basically be 1 inch too big if you're using a 1-inch end mill, because it would cut a 1/2 inch too big on this side, and it would cut a 1/2 inch too big on this side. Okay, because the math is based off the center of the cutting tool. Okay, the center point, or the center of the spindle, some people call it. So that said, you don't want to just go in here and turn this off, because then you're not going to have a toolpath, which you should notice if your toolpath's not right, unless you're just not paying attention or kind of unfamiliar. I mean, when you're new at this, you just have to get familiar with everything. But it's a good idea to look at your toolpath it gives you, and always look at the toolpath it gives you. There's never a time when you wouldn't look at the toolpath it gives you. Always look at it and just make sure it looks right. You don't have to simulate it every time. Now I would suggest y'all simulate it every time until you get familiar and you could predict what's going to happen. Then you don't have to simulate it. But always look at your toolpath, because you could have had a typo, and that typo could cause you to crash your machine. I mean, worst case scenario, it could cause you to accidentally kill somebody. If you're on a lathe and you have a typo in your code and you're just not paying attention and you generate a toolpath and you don't even look at it, and you're just blindly you're blindly posting code without not even looking at if your code's right. It's like driving with your eyes closed, And you go put that code on the machine and somebody sets the tools and goes to run it. And if it's this is worst case scenario. And the toolpath is really, really, really bad, actually on a lathe, it doesn't have to be that bad. But if it's a bad toolpath on a lathe, you could knock that tool out of the chuck jaws, okay? Depending on the weight of the part, and if it gets projected from the machine, it could hit somebody and kill them. So always look at the toolpath it gives you. All right, and especially when you first start writing programs for lathes, you need to double check everything you do, because it's like driving. When you first start driving a car, well, anytime you drive a car, when you cross the intersection, you need to look both ways. You need to look to make sure, there's nobody coming before you pull out, you need to make sure the light's not red or yellow. Same thing. You need to look at your toolpath. Don't just blindly hit OK and think you have a toolpath. Look at what it gives you. Okay? You don't have to simulate it every time, which is a good idea to simulate it. But definitely at least look at the toolpath it gives you. But I would suggest simulating. I don't simulate every toolpath, but I also use the software every day. And I'm familiar with the toolpaths, and I'm familiar with everything, that it's consistent, I can predict what's going to happen most of the time. But anyways, that's how you put a wear in there. So you get a face, you got a 2D pocket, which we're using that operation or that toolpath as a roughing operation to rough all that material out. And we got 2D contour, which we're using as a finish pass. Now, 2D contour isn't always finished. I'll show you all some other applications next class, but yeah. So you got a face, facing, pocketing, and contouring. All right, so that's your main 3 operations you're going to use on it. Well, okay, your main operations, there's 4. You got drilling too, but we've already covered drilling, and I think everyone's got that. You should have that. If you're still having trouble drilling, let me know if you're having trouble drilling. I'll give you a stack of exercises that you could just keep writing drilling programs until you get it, which you should have it down after the 3rd one. Drilling's pretty simple. Now, when I say after the 3rd program you wrote for drilling, that's assuming that you did it in a timely manner. Like if you write a drilling program, if you don't use the software for a couple weeks, and then you go do another one, if you don't use it for a month, and you go do another one, yeah, you're probably, that time, that space and time, it's such a, you're not going to remember. I remember your brain, how you learn stuff and how the brain stores memories. It's repetition and time. Okay, so if you use Fusion 360 1,000 times, you're going to be familiar with it. Now, if you use Fusion 360 1,000 times, but for only 5 minutes once a week over a 10-year period, a 3-year period, yeah, you wouldn't really be good at it. You want to hit it and get that repetition back to back, in a reasonable amount of time. But with that said, these are our main milling toolpaths. The other ones, they're going to take up more time. They're not really complicated or anything. They're probably all equally as simple toolpaths. Adaptive clearing might be a little bit more advanced. It's a little bit more advanced than these. Drilling is the simplest toolpath. Then facing, and when I say simple, I mean you could literally select a tool and hit OK, and like you could almost blindly write a tool, create a toolpath off it. I mean, you can do it hyperbolically speaking, you can do it with your eyes closed, right? But basically, the chances of inputting the wrong data are slim. You can literally select a tool, tell it how deep to go, hit OK, you're done, and it will generate a usable toolpath for you in most cases. 2D pocket, 2D contour. There's other limitations that come up, you know, with tool clearance or tool reach or, you know, lead in, lead out, stuff like that. But yeah, these are the basic milling tools.